Hello everybody, welcome to Thermodynamics Lecture 23. Today I'm going to be talking about transient analysis and finishing up chapter 4 of our class. So hopefully we can get through this today, and this is actually one of the more difficult subjects in thermodynamics to deal with because it involves control volume, but control volume that actually has changes as well. So it's something that we are going to figure out today and hopefully do some homework assignments and you're seeing my emails pop up and do some examples, and hopefully we can really get to the bottom of this and we can move on to chapter 5 later this week or next week. Okay, so let me the first things we've been doing here, these video lectures, are looking at the survey results. So I look at the survey results from Monday. And the question was, which one of the following is true about pumped hydro systems for electricity generation? Okay, so I gave a little side discussion on pumped hydro systems and talking about the thermodynamics of those systems, and did an example in class. I also posted that example on the canvas so you can see that. So the answers here are: the power required to pump water through to the upper reservoir is greater than the power generated by the turbine. That was what we found essentially, right? And that if you have a system that you are spending energy to pump water up into a reservoir, essentially what you get back is not the same amount as what you put in. And we're going to learn all about that. This is sort of we're foreshadowing in the class a little bit here. There are discussion about the second law. Okay, now a couple of you put in this one: the power required to pump the water to the upper reservoir is less than the power generated by the turbine. So just make sure you got this right. You don't get back more than what you put in. Okay, and the potential energy of the water is converted to kinetic energy through the pump. Now this is a little tricky. I could see this one, but essentially we're going to be in through the pump. If we think about the pump as a control volume around the pump itself, we're thinking about just the work that's done into the pump. So actually the potential energy of water is converted to kinetic energy. This doesn't even make sense, because if it would even happen in the turbine. The turbine would be the thing that converts the potential energy into the work. So anyways, there's a couple things wrong with this answer. And then nobody said the potential energy is insignificant between the top and bottom reservoirs. That's just downright silly. Okay, so we figured that out. Now, let's see. So hopefully you are doing okay in the homework. I noticed that by this time it's Tuesday afternoon. About half of you have done the homework assignment. Please try to get the homework assignment done and try to get these things, keep the class rolling, and keep yourself on track for getting homework assignments done on time. I think we can really do pretty well, maybe not as good as we did in the class, but we can do pretty well if we keep up with all the assignments, and I keep up on posting things, and everybody keeps giving me feedback on what I'm doing right and what things I'm missing. Last time for the homework I had a little bit of trouble because I posted a problem that you didn't really have everything for the helium on problem 2. I gave you K, but essentially didn't know what to do with K, so you need to convert K into specific heat, so you could use specific heat in the problem. So I actually added that to the problem, so you should have no difficulty of doing that. But that was based on a student feedback. So please give me feedback. Let me know what's going on. Let me know if you like the format. A couple of you have even liked my videos on YouTube. If you want to do that, I think that's great. That way I kind of know. I've been looking at the YouTube channel. You see I have it here. I look at it and I look at see who's 2 people have liked my lectures. I hope more than you have liked my lectures, but I see two gave me thumbs ups. So that's great. I mean, I'm hoping to really improve these as we go, and keep the thing going as well as I can. Okay, so let's get into the new material. Today, I'm going to be talking about transient analysis. So transient analysis means essentially that the state changes with time. So not only do we have things coming in and out of the control volume, but we have the control volume itself changing. So that's what we call it transient, okay? Let me do a little thing with the slides here. So first, we have to integrate the mass rate balance so this is just looking at the mass balance, the conservation of mass. So the change in control volume as a function of time is equal to what's coming in, the m dot I, minus what's coming out, the sum of everything coming out. So essentially this becomes if you integrated it from time 0 to a final time. So we're never going to be doing, don't worry, we're not going to solve differential equations in here. So we're not going to be solving ODEs or PDEs or anything like that. What we're going to do is we're just going to be looking at the beginning time and the end time. So beginning time, the control volume has some state. There's steady stuff flowing in. The end time has some final state. Okay, don't worry. Don't worry about solving differential equations. You can worry about that in your next thermal sciences class in 3332, where you'll probably be doing some differential equations. Here, we're not doing any. Essentially, we just integrate this thing, and with respect to time, and you get the following, right? So you get MCV, mass of the control volume at some time t, minus mass of the control volume at the initial time, is equal to the sum of the mass that comes in during that time minus the sum of the mass that leaves that in that time. This makes total sense to me. Hopefully it makes sense to you as well. So this just says where MI is the amount of mass entering the control volume. MI would be inlet, not initial. Say this will be inlet. And then ME is the mass exiting the control volume through the exit E from time 0 to t. Okay, so all we're concerned about is the beginning and end state. Okay, let me just do an example. You think, oh, what kind of problem do we have that might exhibit this sort of feature? And let me just get my notepad back up here. So essentially, if we think about it, the kind of problem, maybe a really classic example of this is when you have when you're, say, blowing up a balloon, right? So imagine you've got a tank, some gas cylinder, and so it has a valve on the top with some things, right? And you have a tank of helium, right? And you're going to blow some helium balloons for the kids, you know? So here's my stick, kids. Well, I have 2 kids, so I'll put them both in there. So I have to be fair. I have to get my daughter here and my son, and they both want balloons, okay? And then, so then essentially what you got is a line that comes from this high pressure tank, and like a tube, right? And there's a valve maybe here. Okay, so there's a valve. Oops, what happened to my valve? So there's a tube and a valve. Right, and then and then at the end here's a little nozzle, and then you're filling up a balloon. Right? Right, so there's some air kind of flowing, or I'm sorry, helium flowing into this balloon. We'll just say blowing up a balloon. Now what we do in this case is we're thinking about the balloon itself as our control volume, right? So here's the control volume is around the balloon. Now it has something coming into it, and the volume itself of the control volume is changing, but it doesn't matter. Essentially, from the sense of the mass, it doesn't matter at all, right? So in the case where the mass of the balloon was initially 0, essentially we can say that if we were to use the same analysis, right? So we'll go back to our equation here, and we look at this analysis here. We can say that the mass of the control volume at, we'll just say at state 2 minus this mass at state 1 is equal to the sum of the mass going in minus the sum of the, oh, sorry, I'm going to get my drawing here, minus the sum of the mass going out. Right? In this case, there's only one thing coming in, right? So there's just mass coming in. So mass flow coming in, or there's just some overall mass coming in. So then you can say here that, so assume that M1 is, for balloon, assume that M1 is 0. So we'll just say that the M2, the mass of the balloon, or the mass of the helium that we put into the balloon, is equal to the sum of the mass we have, mass we put in, because this guy goes to 0, and we'll assume that the mass is empty. Right? So this is the classic kind of example, right? So we can also decide what the change in volume is, what the work is, and all this stuff, right? So obviously there's some change in volume of the balloon. And it's not a rigid tank. So so this is some gas cylinder. I'm going to say gas. In case you can't understand what my drawing is. If I can't spell, that'd be good. Okay, so that's good. So then we have mass gas cylinder. All right, now this is pretty obvious, right? So this means that the mass of helium added to balloon or MI is equal to the mass of helium at state 2, the mass of balloon at time t, minus the weight of the balloon, of course. I mean the mass of the helium in the balloon, right? Okay, so now the next thing we have to talk about there, okay, so that's real simple. That's just conservation. Oops, that's just conservation of mass. Now thinking about the next thing was we have to think about what happens with the energy balance, or the first law. So we're going to take the same kind of approach, right? So you'll take the change of energy, which is this just du term. So du dt, then the transient time changing energy equation, du cv dt dt is equal to the integral of heat during that time, so q dot dt, minus work that's done, so w cv dt, plus the stuff coming in, the energy, the enthalpy of the stuff coming in. And so remember the enthalpy. So we're using U. Notice rather that we're using U here, which means the internal energy of the stuff. And here we're using H. And I'm going to ask you a question, and you're going to think of the answer to yourself, okay? Why are we using H when it comes to the stuff going into our control volume and leaving our control volume? Okay, think about it. Okay, flow work. Remember flow work. So H equals U plus PV. So in this case, we're using H because it accounts for both the internal energy of the stuff coming in and out and the flow work, the pressure times the specific volume acting on that tube that's going into our balloon. Okay? So when we integrate this whole thing, and when the specific enthalpies at inlets and outlets are constant with time, that's important because if the thing is changing, if the inlet and outlet enthalpies are changing, say for instance you have a temperature ramp or something like that happening, forget it. You can't use this analysis. You have to go back to the integral form. However, all the time in this class, we're going to assume that this HI and HE are constant. Okay, they're not changing. It's the same kind of gas coming in and leaving. Okay, so don't worry about that. So so then we have our final equation. So U CV dt, U of the control volume at some time t minus U of the control volume initial is equal to the heat added minus the work that you get out plus the change in the total amount of mass times the enthalpy going in minus the mass times the enthalpy leaving. Okay, so that's the final equation for our transient analysis. All right, so now if we go back to my balloon example, here. All right, so now imagine that this balloon is at some temperature, right? And the ambient is at some temperature, right? So it's a temperature ambient. Imagine this thing is cold. I mean, usually there's some temperature drop across this valve, right? There's some DT across this valve where this stuff is cold. So that happens, and we can actually talk about that, a throttling effect. When we actually look at throttling, you can see there's a temperature drop. Okay, and then, all right, so now if we were to look at the first law analysis here, we would say that the change in, so say U2 minus U1 is equal to Q minus W plus the sum of MIHI minus the sum of MEHE, right? And that's the equation that we have here. So so U2 minus U1 equals Q minus W plus the stuff going in minus the stuff leaving. Okay, so now we have that in our example. Now I'll say, all right, so one thing that's interesting is that we have a PDV term, so our control volume is actually changing as a function, so we can't negate this. But let's assume here that you've got a adiabatic system. So in this case, we'll assume adiabatic. okay? Even though there's probably some temperature difference between the ambient temperature or whatever. And then essentially you assume that U2 minus U1, so assuming that the stuff in the initial stuff is U2 minus U1, which is the ambient temperature, and we'll say there's some work, so we'll have minus, so the control volume is actually there's gonna be some PdV work, because there's some changing volume in our balloon. It's going to take about that equal, we'll just assume it takes kind of equal amount of force in order to pump this thing up. Plus, this goes to 0 because there's nothing leaving unless we have a leak in the balloon, which would really bum my kids out, right? They'd be sad if there's a leak in the balloon. Okay, and then we can essentially include the term for the energy going in. So MIHI, which is the amount of stuff going in. So then we're going to assume here minus PdV plus MIHI. So yeah, so essentially we'll assume that the change in internal energy equals PdV MIHI. Now, if we assume that the temperature is pretty much constant, right? That the temperature, if we assume that the temperature is constant, then we can say this is 0, and then we can say PdV equals MIHI. And in this way, we can maybe solve for the volume, right? All right. That's a cool example. Maybe we'll save that for an exam or something. I don't know. All right. So there we go. So this is an example of how you might do a transient problem. So notice that we're using this form of the energy equation, right? So essentially, you've got this change of the control volume, and then you've also accounted for the stuff entering and leaving the control volume. Okay. All right. Hopefully it makes sense to you guys. I wish I could ask you questions. One problem with this pre-recorded lecture is that you can't ask me any questions during lecture. But make sure you ask me any questions you want. I'm going to have office hours tomorrow, so you can attend those from 1 till 3, or you can, tomorrow or Wednesday during the day of this lecture. Then let's make my kids happy again. Sorry, just have to do that. Okay, and so please, yeah, ask me any questions about this. But let's do a couple examples. Maybe we'll really solidify our knowledge if we do some examples, okay? So let's see. Let's start with the first example here. These are also in my slides that you can see, and I will post, of course, the answers to these example problems as I usually do. Okay, so now what we've got is an example where we have a rigid tank that has a known volume of 2 meters cubed, initially holding air, so it's an ideal gas problem, remember, at 1 bar, 295. So notice it says rigid, so this is not a balloon problem, right? So it's a rigid tank. Is connected by a valve to a large vessel holding air at 6 bar, 295 K. The valve is opened only as long as required to fill the tank with air to a pressure of 6 bar and a temperature of 350 Kelvin. Assuming the ideal gas model for the air, determine the heat transfer between the tank contents and the surroundings. Whoa, okay. This sounds really complex, right? But it's really not that bad. So we'll say, what do we know? I should make sure I got the right pen here. So we have a rigid tank with air filled from a higher temperature source. Okay, that's all you gotta do. So we're going to find here in this case, find the Q. So Q, we're going to find Q. The heat transfer, does it say in what? In kilojoules. So this is Q, right? Q dot would be kilowatts. Q is kilojoules, okay? So that's what we got to find. All right, now the best thing to do is to write our assumptions. So writing our assumptions, we find here, one, we're going to assume that ideal gas, air is an ideal gas. Notice it doesn't say in the problem they use constant specific heats, so we're not going to do that, okay? We're not going to be given specific heats. We're not assuming constant specific heats. Two, we're going to assume that is we're going to assume that the big tank or the source remains constant. meaning it's always at 6 bar and whatever that is, 6 bar and 350. At 6 bar 350K. Like it's so big that the little tank, it's insignificant, right? The little tank doesn't see any change. During the time of filling the little tank, it doesn't actually see any change. Okay, the ideal gas model for air, heat transfer of the tank, so it's non-adiabatic, of course. And the control volume, let's see, anything else you can think about the control volume? Well, we're assuming that it's a rigid tank. Rigid tank. So the work equals 0, right? So there's no work being done. You're going to change the volume and there's no propellers or anything. So we're assuming that there's no work. And we're also assuming delta PE and delta KE are 0. Okay, I've got to assume that. Now I have to have a diagram. So we're just going to assume this is a really big tank, right? So it's a tank, big. So it's a big tank at 6 bar, 350. Okay, and then oops, I'm doing that. Okay, there's a line here and a valve. Remember, I have this valve for my balloon. Okay, and you turn the valve on, and then you go into the little tank. Okay, now we have to make sure that when we're talking about this, so we're filling the little tank. This is just like filling the balloon. We have to set our control volume. So we're going to do this here. Right, and then essentially what you've got is you've got Q, and you have no work because it's rigid, right? And it's not adiabatic, so it's not an insulated tank. It's a tank that has some heat transfer from it. So this is the valve, and this is our control volume. Okay, so now there's stuff coming in. So I guess what we're going to do is we're going to assume for mass. So let's put the analysis is here. So for the mass conservation here, we're going to assume that the dm/cv dt is equal to m dot in, right? Because essentially you've got essentially the change in mass going in. So this is like m2 minus m1 equals the m dot, or mi essentially, right? And so if you take the rate of change versus this one, that's what this becomes. Okay, so then the mass flow rate, or the mass change of time, is equal to that. And so that if we know that how much is coming into this tank on a flow basis, we know what the inlet mass flow rate needs to be. And we also know here that from the first law, that essentially du dt of control volume is equal to du dt is equal to q dot minus w dot, which is 0. So I'll just leave it off. I'm leaving w dot. I'm leaving kinetic and potential energy off too, okay? And then so plus m dot ihi, right? So there's nothing leaving, right? There's no leaks. There's no leaks in this tank. So then we have m dot ihi. So this would be the rate expression version of this. And then essentially, if we just think that hi is remaining constant, which we assumed, right? Because the temperature is remaining constant. Remember, for an ideal gas, the H is only dependent on the temperature, okay? I'm going to say that over and over and over again until you guys get it, okay? I'm sure a lot of you do already have it, but I'm just going to keep on saying it anyhow. Okay, so then essentially what we've got is then for the energy equation, we're going to have M2U2. So the mass of air at the second state, oops, that's not what we wanted to do, minus M1U1, these are little u's now, is equal to the Q that we are interested in plus mi, so shoot, no, because the H is staying the same. So hi times m 2 minus m1, because this is mi, right? That's the mass that we put into the control volume. Okay, so now I think I think we can just solve this thing for Q. So Q is what we need to find, right? So Q is equal to, let me just be good about this and change my page here. So example 1 continued. So when I save this thing, you know. Okay, so then here we're going to rearrange for Q. So here this is where we used our mass conservation here, right there, to substitute M2 and M1. So then all we have is M1 and M2, and then we actually can do that because we know what the volume is, right? Because we're given the volume and we can calculate what the mass is. Okay, so here we go. Rearrange for Q. We end up getting something that looks like this. So Q is equal to M2U2 minus M1U1 minus HI times M2 minus M1. Okay, so now all we got to do is figure all these different things out. So HI is definitely pretty easy to find, and U2 and U1 we can find in the tables as well for air at the different temperatures because we know those states. Let's see. Yeah, so I think we're good here. So initially that's at 295. All right, so let's just come up. So we don't know the masses yet. So what are the masses? So let's see. We're going to use our friendly ideal gas law. So M1 equals what is it? P1 V1 over RT1. In this case, we're just going to go here. This is, so the initial pressure in the tank is at 1 bar. So we're just going to say this is at 100 kPa. And let's see, we have 2 meters cubed, right? Did we say 2 meters cubed? 2 meters cubed. 2 meters cubed divided by, oops, make sure this is right, 8.314, which is the ideal gas constant, divided by, what's air, right? So we're going to say 28.97, and we're going to have 295, which is our initial temperature, right? T1. So if we do this here, we get 2.36, yeah, it's 2.36 kilograms. Okay, similar for mass 2, we know P2V2 over RT2. And this is equal to, so at the second state, we know we've equilibrated, right? Doesn't it say we equilibrate? Connected to, fill the tank with air to a pressure of 6 bar and 350, right? So, yep, air at 295. So you notice that there's a difference in temperature here. You notice there's a difference in temperature between the large vessel is at 292. Sorry, it's at 295, and the temperature inside the vessel is 350. Why do you think that is? You think about it. Well, we're doing some work. We're doing some flow work to actually put that stuff into that tank. So you're actually heating the gas inside that tank. Isn't that interesting? So essentially, even though the large vessel is at the same temperature as the small vessel initially, the flow work, the PV work, is actually adding energy to that tank. It'd be really interesting to derive that. Maybe if you have a chance, you can derive that. Actually, thinking about it, that's a qualifying exam problem that I gave a few years ago for PhD qualifying exam. So just to let you know. So that so this is stuff that you're gonna need to know if you go to grad school. It's something you might want to remember. Okay, so let's see. Let's see, P2, V2, okay, so let's do this one. So this is 6 bar, so that's at 600 times the same volume, 2 meters cubed, 8.314 over 28.97 times, and this was at 350K, and this gives us 11.95 kilograms. Okay, so now the only thing we gotta do is then find everything. So from A22, so we need to find, from table A22, we need to find the properties. Okay, so we need to find, first thing we need to find is U1 is equal to, little U1 is equal to 210.49 kilojoules per kilogram. This is at what does it say, 295? Yeah, 295. 295. U2 equals 250.02 kilojoules per kilogram. And this is at 350. And then HI is equal to H at 295, which is 295.17 kilojoules per kilogram. Okay, so then all we got to do is find our answer. So Q then is equal to 11.95 times 250.02 minus 2.36, which is the initial, times 210.49 minus 295 times 11.95 minus 2.36 was the change in mass. So let's see, 295. Yeah, 295.17, but close enough, right? This is the 295 from there, the HI. And then so we just solve this thing and we end up getting equals negative, oh my goodness, equals minus 339.7 kilojoules. Okay, and this is the Q. So this means that, okay, so positive heat is heat in, so this is heat out. This is heat loss. Okay, kind of lose a lot of heat. I wonder if it was adiabatic, what you'd see. Interesting. Maybe we could solve that problem. You can see if this was an adiabatic tank, what kind of temperature would you achieve? Okay, but anyways, that's not the problem. So here we are. So anyway, so that's the first example that we're going to do. Okay, so for an ideal gas, you can see it's pretty reasonable. You've got this big tank at 6 bar 3. Oh, I made a mistake here, didn't I? Nobody's around to check me here. This is at 295K, and then this is at T1 equals 295 and T2 equals 350K. All right. Nobody said anything. Well, okay. Nobody can say anything. I always make mistakes, and you guys always correct me in class. Okay, but I think I got it now. All right. So there you go. There's your example, and let's move to the next one. So let's go out of here and let me look at example 2. Okay, so this is another one. So this is the same problem, okay? I meant to do this exact same problem, but this time I want to do it with a gas that's changing state. So like a phase change problem, a two-phase problem. So in this case, we have a volume of known, okay, initially containing ammonia at 20 degrees C, 1.5 bar. It's connected by a valve to a large supply carrying ammonia at 12 bar, 60 degrees C. So now the temperature of this other stuff is hotter, okay? The valve is open only as long as required to fill the tank with additional ammonia, bringing the total mass of the ammonia in the tank to a higher mass. Finally, the tank holds a two-phase liquid vapor ammonia mixture at 20 degrees C. Now it's getting a little more complex. Determine the heat transfer between the tank contents and the surroundings in kilojoules. So it's the same problem as what we had before, essentially, except now you have this flowing thing, and you've got phase change and all that stuff. So let's figure this out. Okay, so let's figure this out. So yeah, so known. We have a rigid tank with ammonia. Filled from a high pressure source, right? And then we've got a same objective. So the objective is to find the heat transfer, find Q in kilojoules, right? Okay, so we found the Q in kilojoules. Now I guess what we're going to do is we've got to do the same assumptions that we did before. No, we can't assume ammonia is an ideal gas because it does say two-phase, so we can't do that. We can say one, we have a rigid tank with no, so there's no work. The change in kinetic energy is essentially 0, and the change in potential energy is equal to 0. Okay, so there's no drop or anything like that, so that's not changing. So 2, we can also assume this is a steady state, so the properties of ammonia entering are unchanging. Okay, so we assume that we have an unchanging situation with regards to the tank. So now let's make our diagram. So let's make our diagram here. So we've got stuff coming in here. So we've got a big like pipe. We've got a so we have a big pipe here, and we've got I kind of made that wrong, didn't I? Okay, so there's a big pipe here, and there's flowing ammonia. Oops, go back here. So there's ammonia flowing in here, right? So there's ammonia at 60 degrees C at T equals 60 degrees C. And is there a pressure given? Let's see, pressure 1.5, 12 bar. Okay, so 12 bar. I bet that stuff is superheated. If it gives you temperature and pressure, you can pretty much assume that it's superheated. And then here you're going through another valve. And here you're going into a another vessel like we did before. And this is our control volume here. I'll say, so here's our smaller vessel. Here's our control volume. So this thing is getting filled up. It has some ammonia in there already. So initially containing ammonia at 20 degrees, 1.5 bar. So T1 equals 20 degrees, P1 equals 1.5. 1.5 bar. And then M2 is equal to how much? 143.36. That seems very specific. 143.36 kilograms. We don't know T1 and P. We don't know P2 and T2. So we're gonna have to figure that out at some point during the problem. Okay. But oh yeah, I guess we're gonna have to assume that T2 is equal to the same, because if it's a two-phase liquid, it's probably staying in the vapor dome. Fill the tank with additional and bring the total mass. Finally, the tank holds a two-phase liquid vapor mixture at 20 C. Okay, so this is, we do know T2 equals 20 degrees C, and it's two-phase. Okay, so it's 20 degrees two-phase stuff. So we could probably, we can definitely find the pressure then if we know the temperature. Okay, so now let's do the analysis here. Now for the problem, we're going to assume that we have the same analysis as we did before, right? Because it's the same, kind of the same problem we did before. So we'll just say same as example 1, where we have essentially that m dot I equals dmcv dt, and so m in is equal to m2 minus m1, right? So that's what we've got there. And then essentially, so example 2 continued. All right, so then we have here the next thing we have to do is the energy equation. So we're just going to say we're going to use the same thing. So Q equals m2u2 minus m1u1. Oops, make sure you get that right. u1 minus hi m2 minus m1. Okay, let's just, that's a 1. Okay, so let's just assume that we have the same equation from before, because that's what we've got. There's no work, right? So we said the work and the kinetic energy terms and all that stuff are 0. So now let's see, what are we going to do? We're going to find the thermodynamic states. Find the states. Okay, so let's see. Let's find from tables. So we have to find the ammonia tables, right? Let's see if we can find which one it is. So ammonia table, we need to find for condition 1. I think we've got two-phase stuff. I'm not sure. So we have to find from state 1 is T1 equals 20 degrees C and 1.5 bar. So let's go check it out. So let's see here. I'm going to go back. I'm going to find our tables. We have time? Yeah, we have some time here. Let's take a look at it. So if we look at our tables here, let's find it. This is the wrong thing. That's not what I'm interested in. Table of contents. That's what I want. So index, we're in SI units. We're going to look for ammonia. And let's see. Let's assume 20. So they're giving us temperature and pressure. So I'm going to go and look for superheated and see. Well, if it comes up, that would be good. Here we go. What is this? Is this ammonia? Trying to find ammonia. Oh, that's R134A. Let's find ammonia. Here's ammonia, right? Let's see. Let's look at superheated. It's probably the first thing to do. What happened here? Here, let's go. Ammonia. Here it is. All right. Move myself over here. So we said 20 degrees C, and what's the pressure? 1.5 bar. So 1.5 bar. Tsat is negative 25.22. Oh, we're vapor. Negative 25.2 at that pressure. So even at a 1.5 bar, this is going to be vapor in there. So Tsat is 25. So we got to be a little higher pressure in order to get. So we got totally vapor in there. So at 20 degrees C here, we can just copy these values, right? So I'm just going to copy these values over. So from table A15, here I'm going to leave the table on there. So A15, we're going to go here and just put in our values. So V1 equals, what is this? 0.9382. 0.9382 meters cubed per kilogram. We're going to need H, right? I'm not going to use U1. Let's get everything. So U is, so if we look here, U is the third column and H is the fourth column. So at 20 degrees C, this is 13. Here we go. Just kind of highlight these. Let's see. Oh, it's not going to let me do that. All right, sorry. We can't highlight them. It's not letting me do it. U1 is 1371.79 and kilojoules per kilogram. And H1 is equal to 1512.51 kilojoules per kilogram. Okay, so then let's see. Let's state 2, it's two phase, right? So it's state 2. Okay, so let's see. State 2, we're at two phase. So we have to look here at where we're at. So we have a given mass, but we know we're at two phase at 20 degrees C. We could probably find the volume. We know the volume, right? Do we know the volume? Yeah, we know the volume is 0.5. So we know the volume. So V equals 0.5 meters cubed. So we know what and we should be able to figure out the mass, right? Because we should be able to figure out the mass because we know what it is in the first one, right? So like, so we're going to be able to find the mass of 1 is equal to the total volume over the little volume 1, and this is equal to 0.5 divided by 0.9382, and this gives us something like 0.533 kilograms. All right, and then kind of moving on, so then M2 is known, right? What did we have? M2 is 143.36, a very accurate number. Right, and so then we know essentially what V2 is equal to V2 over M, right? And so that we know that V is 0.5 over M2, which is 143.36. and this is equal to 0.0035 meters cubed per kilogram. And now we need to look at the table. All right, so now I'm going to go back to the tables, okay? So I'll go back to the tables and look at saturated. So we know it's saturated ammonia. Saturated ammonia at, did we say? We said 6 bar, right? Let's see. No, let's see. Find the tank twofold. No, 20 degrees C. So we have to find the temperature table. So ammonia temperature table is here. 20 degrees C. We have pressure is 8.5762. So this is table, looking this A13. So P2, we know because we know it's saturated. So if we know the temperature, we know what the pressure is. It's 8.5762 x2 bar. So we know V2, and let's see, let's just copy down these things that we know. So what are we going to have to find? We're going to have to find VF and VG. I'm just writing what we need to find. So VF and VG are here at 20, we're at 0.00163. And VG, 16386. Oh my god. Okay, here we go. 86, and VG is equal to 0.1492. How are we doing time-wise? Okay, I'm fine. And then essentially we're going to need to know, what else we're going to need to know? State 2, we need to know the U, right? I don't know if we need to know H. No, we don't need to know H2. We just need to know U2. So U, F is equal to 20 is 272.86. Okay, sorry, I'm just copying down from the tables, and I'll just go back to my notes here. And then UG is, so UG then is, oops, I have to go back because I have to look it up. So UG then is at 20 degrees C, 1331.94 kilojoules per kilogram. Okay, so what we can do then is, all we have to do is we have to find the quality at 2, right? So we need to find X2. Okay, so let's go back. So example 2 continued, and then essentially find X2. So X2 in this case, so X2 is equal to V2 minus VF over VG minus VF, right, which is VFG. And in this case, we can put our numbers in. We can put our numbers in here. I'm not gonna do it because I don't want to spend all this time. But essentially, V2 is 0, as we found, 1 point. Here we go, 0.0035 minus 0.0016. What is it? 16386. Divided by VG minus VF, so 0.1492 minus the same thing, 6386. And so we get the quality is something like, 0.0126 or 1.26%. It's pretty liquidy stuff. In there. 1.26, not very high quality. So then we can find U2. So U2 is UF plus X UFG. And so then U2 is equal to 272.86, which is UF, 0.0126, which is the quality, times the difference in the internal energy, which is 1331. We'll just say essentially 1332 minus 273. Okay, and this ends up being U2 ends up being 286.2 kilojoules per kilogram. All right, so then all we got to do then is substitute this guy in, right? Because we know what the H coming in, because we've already done that. H coming in is this stuff up here. Did we actually find H coming in? So state 1, H1. No, we didn't, but we could find that because that's directly from the tables. So you can find it. H coming in. HI is. Wait, I have it written down here somewhere just to make sure. This is HI actually. So this is at HI. From A15 at at the temperature and pressure. So at the line T and P. Okay. So then if we go down here, we can find the final answer. So Q is equal in this case to 143.36, which is that mass, times 286.2, which is what we just found for U2, minus the initial, which is 0.533 times 1371.8, essentially, minus the mass, which is what is it? I have it written down, 1553.07, which is the H, which is here because I had a squared one, right? 0.07 times the change in mass. So the change in mass is 143.36 minus 0.533, which is the initial mass. Okay, so now we find the Q. So essentially it's the same problem as with the air, except that we're just doing with a two-phase fluid. So this ends up being 181,522 kilojoules. And then here's the heat out. It's useful to say where the heat is going, in and out or whatever. It's useful to say. It's useful to do that. So, okay, I think that's all we needed to find. So heat transfer to the surroundings. All right. So hopefully you understand this. If there's any mistakes in this thing, I'll make sure to correct it. But I think we're good to go on this one. So I'll post these examples to the Canvas, and then we'll move on from chapter 4. So if you have any questions on transient analysis, please let me know. Otherwise, we'll look forward to seeing you again on Friday. Bye.